So we've figured out a sampling method, and now we're going to move on with this, getting a confidence interval for what percent of the high school youth have had a concussion. So whether we did a simple random sample where we simply gave everybody an equal chance of being selected, put names in a hat without replacement, and or we did a stratified random sample where we knew we had different groups of people. Maybe there were a whole bunch of these purple people, and therefore we needed to get proportional representation from each of these different groups. So we're going to randomly select some from each group, and we're going to get twice as many randomly selected people from the purple group as we do from the other groups because of the fact that there are more of them. Okay? Or we use a cluster method, which is also grouping, but it just happens to use natural geographic groupings from this population, and we randomly select one or more of the groups and we survey everybody in that group. And that works if those groups are representative of the entire population. Or we use that systematic one, that robotic, find a starting point and then get every third person after that kind of thing. Okay. So once we finally got that, how are we going to do this confidence interval? They're asking us to build a 98% confidence interval for this proportion of people that have had a concussion. And so under state, we're going to simply name our procedure. So this would be a one sample confidence interval for proportions, or a one sample confidence interval for proportions. All right. And then we would define any kind of values. P is the true proportion of people that have had concussions. We're going to eventually use this formula with p hat in it, but let's look at some detail. We're going to plan. We're going to check for randomness. That is a condition for just everything we do. Were they randomly selected? Yeah, maybe we used an SRS or whatever. So it's generally stated in the problem. If it wasn't, I would be very cautious. Maybe say proceed with caution, wasn't stated. But if it's not stated, then make sure you say that. Don't just SRS or random check. Go and identify if it's in there or not. Normality, we're checking for what we call large counts. Were there enough successes and failures? So here, maybe we found 138 students out of the 1,382 that we happen to ask. That was convenient, nice little 10% deal. That had a concussion in the past, and so we check that and we make sure that the successes and failures was greater than or equal to 10. We also want to make sure that we have the 10% condition matching, that our population is big enough to support this sample, or the sample's not too large, encroaching upon the size of the population. And that is, we assume over, well, if we got 1,382, then we have to assume that we have 1,082 and throw a 0 on it, so 13,820 students in Georgia, and that is a fair assumption. All right, so if the conditions are met, then we move on. If they're not met, then, well, proceed with caution. The next step is to do. Our favorite part of it is just do the mathematics. Here's a little something already pre-made. Let's see what components we have. We've got p hat plus or minus z star, so we're always dealing with z star for proportions. And then so this is called our point estimate. It could have been an x bar if it was a mean, or it could have been actually a slope, a lowercase b slope from our sample if it was a slope confidence interval. But we got z star, and that's good for proportions. And then we've got this standard error of this statistic, or this point estimate, and that's p hat 1 minus p hat over n, all square rooted. So here's our value. It's just about 10%, and plus or minus, we got this z star straight off of the chart. I went to table B. At the very bottom, there's this little infinity row, and below that it has percentages, and somewhere on there there's 98% column. And in that row with infinity on the t distributions is the z star values, and must have had 2.326 there. Okay, you can also get that through a calculator or z-score table, but that I find that to be the easiest place to get it. And then eventually we just come out with these two. So we're saying I am, let's save it for the next one, the conclusion. I am 98% confident that the interval 0.08109 to 0.11862, in other words 8% to about 12%, contains a true parameter proportion of students in Georgia that have had a concussion. It's our inference for all students in Georgia, and that's valid if you've done a good random sample and it meets all those conditions. So that is your confidence interval. Let's take a quick look at, well, what if we had done, if we were estimating the length of the concussion? Well, now all of a sudden it is looking at the parent population being normal is not, so this is under a mean and not a proportion. Now we're looking at n greater than or equal to 30 if the parent population's not specified to be normal. If it is less than 30, then we need to look at some graphs and try to find out if there are any obvious signs of non-normality that would make us want to proceed with caution, or if everything looks okay. And here's the formula. X bar plus or minus Z star. Ooh, well, to do Z star, you kind of have to know the true population standard deviation, and we probably don't know that because it contains the true mean, mu, in that calculation, so I don't think we're going to know that. So we're going to have to punt from the Z star stuff, and we're going to have to use this T star and the T distribution table. So we're going to go with degrees of freedom of n minus 1, however big our sample was, and then we're going to go use the chart and figure out what to put there. Let's see, and then I might as well address this last one in here. All sticking with confidence intervals, our newspaper editors wants us to reduce that margin of error to 1%. So we take the back portion of this formula, instead of the p hat plus or minus, we just take the Z star times the standard error, and we set it less than or equal to 0.01. I like to just set it equal to and then just solve it for n, and then just round up in the end. So this is what I got, but I need to round it up and just say, hey, I need to get at least this size to get that margin of error down to 1% or less. So just be prepared to do that. If it would, for means, it would use the same formula that we did for the confidence interval for means, but we would just grab the back part of that and then set it equal to the limitation that we have in terms of margin of error and solve again for n. All right, thank you.